So as we try to better understand how carbon dioxide and oxygen are exchanged between blood and alveoli, it's really important that we understand a couple of gas laws. The first is Dalton's law, which says each gas in a mixture of gases exerts its own pressure as if the other gases were not present. So the other way to say this is each gas has its own partial pressure, and the denotation for that is P, it's capital P. Henry's law says the quantity of a gas that will dissolve in a liquid is proportional to this partial pressure, as well as its solubility coefficient. Now, its solubility coefficient is its physical or chemical attraction for water, and this is assuming temperature stays the same. So let's just take a quick look at Dalton's law first. So again, this is the amount of partial pressure that one gas exerts as if all the other gases were not there. Now, our atmospheric pressure, as we saw a couple of lectures ago, is 760 millimeters of mercury, and this is due to the combined partial pressures of oxygen, carbon dioxide, nitrogen, and even to a certain extent, water vapor. Now, the air that we breathe in, we saw this again a few slides ago, is 21% oxygen, 79% nitrogen, and in some very, very small amount of carbon dioxide. Now, again, these are rounded up numbers, right? If you want more specific numbers, I provide you guys the link and you can get more accurate numbers. But for just our purposes, this is what we're going to use. So let's just say we want to determine the partial pressure of oxygen. So what we do is we multiply that 760 mmHg, so the entire whatever the atmospheric pressure is, by the percent of air that is oxygen. So we simply multiply 760 mmHg by 21%, or 761 times 0.21, and we get 159.6 mmHg. That is the partial pressure of just oxygen. Now, if we did that same thing with nitrogen, so multiplied 79%, or 0.79, times 766 mmHg, what we would get is 600.4 mmHg. And you can see if you add those two together, they roughly add back up to that 760 mmHg. And that's mostly because we are rounding up these two numbers. If we were using the more precise numbers with decimal points, we would also be able to factor in the contributions of carbon dioxide and water vapor. But again, for our numbers, this makes sense. So again, simply you multiply the atmospheric pressure times the percent of the air that gas is. So whether it's 21%, 79%, or 0.04%. Now, Henry's law, again, takes that partial pressure, so whether it's that 600.4 mmHg of nitrogen or the 159.6 mmHg of oxygen, and it takes into consideration its solubility coefficient. So those two things work together whether or not it will actually dissolve in a liquid. So as we saw, and I'll skip over this for a second, so we saw even though nitrogen makes up 79% of the atmospheric air, really none of it actually goes into solution. We do not have gas exchange occurring in alveoli because the solubility coefficient is just so low. You have to greatly increase that pressure to force it to go into solution. Conversely, more carbon dioxide is actually dissolved directly in the plasma. There's actually very little oxygen that's dissolved in plasma. That's why we have to have red blood cells to carry it. But carbon dioxide, some of it does dissolve in plasma, and that's because its solubility coefficient is much greater than that of oxygen. So let's take another look at this Henry's law. So why we care and how it affects us. So remember, we care about partial pressure and solubility coefficient. So as pressure increases, partial pressure also increases, right? Because it's a multiplication of the two. So it particularly affects people who are scuba divers. So at low depths, the pressure is very, very high. It can be much greater than 1 atmosphere. It can be so high, in fact, that nitrogen now goes into solution. Now, nitrogen is not normally in again, in your plasma. So what happens is that this can negatively affect the way your neurons function, causing what's called nitrogen narcosis, or it's sometimes referred to as rapture of the deep, or even the Martini effect. That's because the effect of nitrogen in solution, and you can see this, enough nitrogen goes into solution at 15 meters underwater that it's like you just took like a shot of like a martini. You just had a martini. If you go down to 30 meters, it's the same effect on your neurons as drinking 2 martinis, and so on and so forth, as you can see here. Now, I don't know about you, but after 4 martinis, one right after another, that has a very significant effect on cognitive function. And if you've ever either been drunk yourself or have seen, drunk people, you know that their behavior can become very uncoordinated, and that can be actually very deadly underwater, right? Sometimes people will either get lost, or they even take out their breathing apparatus, and then they drown. So it can be very dangerous. Now, conversely, if you go down, and let's say you're at 30 meters, you can't just shoot back up to the surface either, because again, that nitrogen has a very low solubility coefficient. So if the pressure is not there to keep it in solution, it will want to come out. Now, the way it does that is it'll form bubbles if it happens too quickly. So if the ascent is too rapid, it will actually form bubbles, kind of either frothing the blood, which is bad, or causing bubbles in the joints to occur, which is incredibly painful. But this can lead to death. It can, or some very significant organ failure. You may have heard of it called the bends. That's what you're talking about. So this is why people, if they dive down deep, they have to make enough time to also come up very slowly so that you can naturally just breathe, slowly allow the nitrogen to come out of solution and breathe it out. We can also use this principle of Henry's law to treat certain conditions. So we can actually put people into hyperbaric chambers to cause more oxygen to actually dissolve in the blood. Now, we would want to do this in cases where maybe we're fighting anaerobic bacteria like in tetanus or gangrene. Some people may have some heart disorders, so this forces oxygen to go into solution. Carbon monoxide we'll talk about at the very end. It actually will bind to red blood cells 210 times more strongly than oxygen. If someone has been poisoned via smoke inhalation or asphyxia, by putting someone into a hyperbaric oxygenation chamber, it can quickly get oxygen into solution. Now, we talked a little bit about going into deep water. Well, what about going up a mountain? So remember, at sea level, atmospheric pressure, so this is here in Phoenix, is 760 mmHg, and oxygen is 21% of air, right? So again, we multiply those two together and we get that 159.6 mmHg here at Phoenix levels. So let's say we go up to like an elevation of roughly Flagstaff. Well, the atmospheric pressure is less. It's now, instead of 1 atmosphere, it's less, so it's 0.77 atmosphere, or 585 mmHg. That's the outside atmospheric pressure. So if we now multiply that 585.2 times 0.21, the percentage that is oxygen, what we end up with is 122.9 mmHg. So the partial pressure of oxygen has decreased quite a bit, about 36 mmHg. If we go up to even higher, roughly the elevation of like Snowball, it goes even further. You can see that number here. So again, if we multiply as 524.4 times 0.21%, we get 110.1 mmHg of oxygen. Again, that partial pressure has decreased quite a bit from that 159.6 that we started from here at sea level. And then when you get up to Mount Everest, the atmospheric pressure is much, much less. That's almost half, right? So when we do that math, the partial pressure of oxygen is simply 46.5 mmHg. That is down from, again, 159.6 at sea level. So you can see why, by that great decrease in atmospheric pressure, it will affect the partial pressure of oxygen and how much it will actually want to go into our bodies and be available for our use. Now, there's plenty of people who live at very high altitudes, and I don't just mean like Snowbowl and like Flagstaff. We're talking like there's some very high altitude natives that live closer to that, well, higher than Snowbowl, but I guess lower than Everest elevations. Again, so how do they do it? Some of these people, so we're talking like Peru, Inca, folks like that. There's some high level natives in like Ethiopia. There's some in Nepal, right by the base of Everest. So all of these people who've lived there for many generations, they have certain adaptations. One is larger lung volumes, and by having larger lung volumes, that will allow more air to go in, so that allows for more opportunity for gas exchange to occur. There's an increase in number of red blood cells, and this is true for any of us. So if you all of a sudden move to a very high elevation place, you would not all of a sudden develop larger lungs. However, you will increase the number of your red blood cells. And you can see like those numbers here. Again, you don't have to worry about this 500 million or 800 million, but just be aware that as you go into these higher altitudes, the way our bodies will try to acclimate to that higher elevation is by increasing the number of our red blood cells that are available to us for gas exchange. Natives, again, who have lived there many generations and have genetic specialties to that high elevation. One of these is also a decreased oxygen affinity of red blood cells, which means that the red blood cells do not hold on to the oxygen as tightly, so it delivers it to the tissues much more easily without affecting how it's taken into the lungs. So gas exchange occurs across the lungs, no problem. Red blood cells will pick it up, but they also drop it off much quicker, right? Getting it to the tissues as they need it. If you'd like to learn more about this is actually pretty fascinating about about human evolution to high altitudes. Dr. Cynthia Bial gives a really good talk. It's about an hour, 50 minutes or so, and here's a YouTube link that you can watch. Okay, I hope that all makes sense. As always, if you have any questions, please let me know.